So we're going to talk about molecular shapes today, and we're going to predict shapes of molecules by using what's called the VSEPR theory, valence shell electron pair repulsion theory, where it assumes that all atoms and lone pairs attached to a central atom will spread out as far apart as possible to minimize repulsion. And in order to use VSEPR theory, you have to draw an accurate Lewis structure for any particular molecule or polyatomic ion. So let's start with carbon dioxide. To draw the Lewis structure for a carbon dioxide molecule, the technique we do is we add up the number of valence electrons in these atoms, and that's going to equal the number of valence electrons in the molecule. Now, this is one of the reasons you had to do well on the first test in this class, is because you have to know how to use the periodic table to predict how many valence electrons there are for atoms of any element. Carbon's in the fourth tall column on the periodic table. They always have 4 valence electrons. Oxygen's in the sixth tall column on the periodic table. They always have 6 valence electrons. So this molecule is going to have a total of 16 valence electrons. So once we draw our Lewis structure, that Lewis structure, which shows all the valence electrons, should show 16. In terms of drawing a Lewis structure, you draw a skeletal structure first, where you assume the first element given in the formula is in the central position. Then you use pairs of electrons as bonds to attach that carbon to the other 2 oxygens. Each of those dashes in a Lewis structure represents a pair of electrons, and those electrons attract to both the nucleus of the carbon and the nucleus to the oxygen. That's what holds the atoms together. These 2 electrons here attract to the nucleus to the oxygen and the nucleus to the carbon. That's what holds those 2 atoms together. This skeletal structure is using 4 of the valence electrons so far. We've got to get up to 16. So you're going to put the rest into the structure by completing octets of each of the atoms in this molecule, outer atoms first. So watch this. We've got 4 already. Let me go to the left O. 6, 8, 10. Let me go to the right O. 12, 14, 16. And I've run out of electrons. Those are the 16 valence electrons. I have them all accounted for. Now, Lewis predicted that molecules would bond so that they can achieve a stable outer shell configuration similar to noble gases, which is called an octet. So now you check your structures to make sure all the atoms have octet configurations. If they do, you're done. If they don't, you're not. The carbon here does not have an octet. It only has 4 electrons in its outer shell. So if that occurs, what you need to do is you need to take a lone pair from an atom that has an octet and move that lone pair into a sharing position. That's increased the number of valence electrons for carbon up to 6. It's better, but it's not quite an octet yet. It needs to take another lone pair from one of the atoms that has an octet. So if I take it from the other atom and make it share, carbon now has 8 electrons in its outer shell, and both oxygens have 8 electrons in their outer shell. Lewis would consider this the most accurate representation of the bonding in carbon dioxide. The 2 atoms, the C's and the O's, the 3 atoms, each C and each O, or the C and each O, bond together with 2 pairs of electrons. And that actually causes the atoms to be pulled close together. The strength of that bond is really high. So now if we do experimental testing of carbon dioxide and test the bond length and the bond strength, if the bond length is short and if the bond strength is high, that's indicating that these are double bonds in the molecule, and Lewis theory seems to be predicting these properties of molecules fairly accurately. So now we have our correct Lewis structure. Now we're going to try to predict the shape, and we're going to use the VSEPR theory. What this theory says is that the electrons here, being negatively charged, are going to repel against the electrons here. And so that means these 2 oxygens are not going to want to be close to each other. So they're going to probably, because their bonds repel, they're going to spread out to put those oxygens as far apart as possible. If that happens, then that would be the predicted shape of the molecule from the valence shell electron pair repulsion theory. So we calculate something for the central atom called its steric number. It's how many atoms are bonded to it plus how many lone pairs it has. That number that you calculate is called steric number, and it's going to be abbreviated SN. It's the sum of the bonded atoms and lone pairs on a central atom. Now, it doesn't say the number of bonds. Carbon is making 4 bonds. We're not adding up 4. Carbon's bonding to 2 atoms, so 2. And there are 4 lone pairs in this molecule, but all those lone pairs exist on the oxygens. They don't exist on the carbon. The carbon doesn't have any lone pairs. So the carbon only has 2 bonded atoms and no lone pairs. that means the steric number of the carbon is 2. And that statement can be abbreviated by just saying SN equals 2. So once again, why is that 2? Because there's 2 bonded atoms to the carbon, and there are no lone pairs on the carbon. That tells you how many groups repel against each other, and so they're going to try to spread out to be as far apart as possible. So you just have to imagine, how can 2 oxygens spread out from each other around a central carbon as much as they can? And if you think about it, they're going to have to spread out with an angle between them of 180 degrees, right? If they go like this, they repel, least amount of repulsion if they go like that. So I don't know, Lewis didn't know what the shape of a carbon dioxide molecule was, but people that came up with this idea of the VSEPR theory said, I bet it's going to be a molecule that looks like this. We would call that linear, the bond angle of 180 degrees. Because if the oxygens are going to repel each other, they're going to probably just move as far apart from each other as they can. And in fact, when we actually do X-ray diffraction of dry ice, which is carbon dioxide crystals, we find out that we can determine what the angle is in a carbon dioxide molecule, and it's 180 degrees. It's exactly right. So experimental data has verified a lot of what the VSEPR theory predicts, and that's why we're learning it in this class. All these molecular shapes we're going to talk about today have all been verified experimentally, and that's why we believe the VSEPR theory is a powerful tool in predicting molecular shapes. You have to draw a Lewis structure first, and then after the Lewis structure, you calculate, or you think about a steric number, and then you have to imagine, and Imagineering here, how can those groups spread themselves out as far apart as possible? And if you can visualize that shape or that arrangement, that's the shape of the molecule. So if you actually wanted to draw a carbon dioxide molecule in its proper shape, you would draw it like this. It's completely coincidental that the shape I drew for the carbon dioxide molecule just happens to be how I draw the Lewis structure. The Lewis structure does not tell you the shape. It just tells you that carbons and oxygens bond with double bonds, and they bond in the order O to C to O. But this does not tell you the shape. You apply VSEPR theory to predict what the shape's going to be. So just, I don't want you to start mistaking a Lewis structure for telling you the proper shape. It doesn't. Once you draw the Lewis structure, you have to think about, what do we need to do to predict how those groups are going to spread themselves out? Let's try this boron trihydride. If you want to draw the Lewis structure for this covalently bonded molecule, you're going to add up the valence electrons for the atoms making up the molecule. Boron's in the third tall column on the periodic table, 3 valence electrons. Hydrogen's in the first tall column on the periodic table, 1 valence electron each. And so this molecule would have a total of 6 valence electrons in it. Boron we would assume to be in the central position, so we'll attach the 3 hydrogens to it. The skeletal structure looks like this. And as it works out, that's the 6 electrons that are in the molecule's valence shell. We can't add any more electrons, we're done. Now, nothing here has an octet, right? Well, hydrogen never will achieve an octet because hydrogen's in the first row of the periodic table. Their outer shell is only the first energy level. All there is a 1s orbital. How many electrons does it take to fill a 1s orbital? 2 electrons. So hydrogens will always have a complete outer shell when they have a bond to them because they're making a structure called a duet. Boron, however, is in the second row. We would have expected boron to create an octet, yet oh, look at this. Yes, 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 yes. That means you can hear me? Yes, you can? Okay, so I'm taking it you can hear me now. So if you can't hear me, then use your speaker and shout outs, and that'll really get my attention, believe me. So in this particular molecule here, where we have boron in the central position, and I'm going to keep the chat open so I can see what's happening here. It's working now. Good. Okay, we're back in business, hopefully. If we want to predict the shape of the molecule, this Lewis structure doesn't tell you the shape. This only tells you how the atoms are bonded. To get the shape, we're going to apply the VSEPR theory. So we look at the central atom and we figure out how many atoms are bonded to it and how many lone pairs it has. If we add those together, that's called its steric number. And in this case, the steric number of the boron should be 3 because there's 3 hydrogens bonded to it, but the boron doesn't have any lone pairs. So the shape of the molecule is going to be whatever shape allows those 3 hydrogens to spread themselves out as far apart as possible. So now you have to visualize that, okay? Are you good at visualizing things? How can you spread those hydrogens out so they maximize their distance away from each other? You would do it in a triangle, an equilateral triangle. What's the angle between the hydrogens in an equilateral triangle?
180.
Try again, that's too big. What's the degrees for an entire circle?
60
degrees.
So divide by 3, each of those must be 120 degrees apart from each other, okay? So this would not be the shape of the molecule. These hydrogens would be 90 degrees apart. This is better because they're repelling. They get to be 120 degrees apart from each other. So anytime you have a steric number of 3, the 3 repelling groups will always make a flat triangle like this. A more scientific way to say flat triangle is trigonal planar. So this is the geometry or the molecular shape you would expect from a molecule in which the central atom has 3 atoms bonded to it and no lone pairs, a steric number of 3. It produces a bond angle that's 120 degrees, okay? So if you want to draw the correct geometry of this molecule, you would draw the boron and then the 3 hydrogens attached to it, trying to do the best you can to make an equilateral triangle so that it looks like each of the angles are 120 degrees, okay? So we're just going to work through a bunch of molecules today, see if we can deduce what their shapes are and see if this whole geometry thing makes sense to you. The next one we're going to do is sulfur dioxide. If you're going to draw the Lewis structure for sulfur dioxide, we would add up the valence electrons for all the atoms. Sulfur and oxygen both have 6 valence electrons, are in the same column on the periodic table, so 6 and 6 and 6 for the 3 atoms would make 18. The skeletal structure, you'd put the sulfur in the center, bond the 2 oxygens to it, and then we're going to add the rest of the valence electrons as lone pairs, trying to make octets for the outer atoms first. So here we go. My structure right now has 4 electrons, 4 valence electrons. Now I'll put in my lone pairs. 6, 8, 10, 12, 14, 16, 18, I'm done. And when you're done, the oxygens have octets each. The sulfur does not, which means this is not a correct Lewis representation of the bonding in sulfur dioxide. So you have to take a lone pair from one of the oxygens, move it into a sharing position. Now everybody has an octet. Now, if you notice, I'm not going to make a second double bond here, right? Because the sulfur now has an octet. Everybody has octets. Lewis would say this is correct. I could have, though, taken the lone pair from the right oxygen, so the correct Lewis representation would be writing the exact same structure with the double bond on the right and the single bond on the left. And between those 2 Lewis structures, I would draw a double-headed arrow. That means the molecule possesses resonance and is a resonance hybrid between those 2 structures. What's the average bond order of an SO bond if this molecule possesses resonance? What a question, huh? So this molecule possesses resonance. You could have a double bond, single bond, or single bond, double bond. What's the average bond between the S and the left O? What's the average bond between the S and the right O?
1.5.
It's the average of a single bond and a double bond. You would have 2 1.5 bonds is what the real molecule would be. We just have to say it's the average of those 2 structures. Now, when we experimentally measure the bond strength of the SO bonds in this molecule, it comes out the strength of a double bond, which is not a bond and a half. This is not correct. So even though we've obeyed the octet rule, making a resonance hybrid of 2 perfect octet structures, this molecule still doesn't match experimental data very well. And the reason it doesn't is the central atom has d orbitals in its outer shell. Sulfur's from the 3rd row on the periodic table. And if you're in the 3rd, 4th, 5th, or 6th row on the periodic table, you will have electrons in your outer shell on your s and p orbitals, but you're going to have some d orbitals in your outer shell that are empty that you can use to exceed the octet rule. And quite often, these central atoms that can exceed the octet rule actually really do that. Here's how you tell. You calculate their formal charge, which is its natural number of valence electrons minus each individual bond it's making minus each individual lone pair electron it has. So let's try that. For sulfur, it naturally has 6 valence electrons. To calculate formal charge, you then add up each bond it's making, not 2 bonded atoms, but in this case, formal charge, 1, 2, 3 bonds. And then it has 2 lone pair electrons. So the formal charge calculation is 6 minus 3 bonds minus 2 lone pair electrons. 6 minus 3 minus 1 gives you positive 1. 6 minus 3 minus 2 gives you positive 1. So the sulfur has a positive 1 formal charge. Let's do the left oxygen. Oxygen naturally has 6 valence electrons. The left oxygen in this structure has 2 bonds that's being made to it. It has 4 lone pair electrons. 6 minus 2 minus 4 is 0. Structures with atoms with 0 formal charges are supposed to be the most accurate. So that's really good. This oxygen is 0. Let's do the right oxygen. 6 valence electrons minus 1 bond minus 6 lone pair electrons. 6 minus 1 minus 6 is negative 1. So in this structure, the sulfur has a positive 1 formal charge and the oxygen has a negative 1 formal charge. This is why the structure does not match experimental data. That central sulfur has a positive formal charge and there's another atom in the molecule that has a negative formal charge. You want to try to get those formal charges from +1 and -1 down to 0 and 0. And the way you do that is you pull a lone pair from the atom with the negative formal charge and make it shared with the atom with a positive formal charge. Now, if sulfur did not have d orbitals in its outer shell, you can't do that. But because it does have d orbitals in its outer shell, it can use its d orbital to bond to this extra lone pair. And this structure now, the formal charge of the sulfur is 0. Think about it, 6 valence electrons. Now it has 4 bonds, 2 lone pair electrons, 6 minus 4 minus 2 is 0. And the oxygen on the right has now gone down to 6 minus 2 minus 4 is 0. All the atoms have 0 formal charges. So the moral of the story is, and you'll see this on homework 2C that's due tomorrow, once you've drawn the Lewis structure for a molecule and it obeys the octet rule, if none of the atoms can exceed the octet rule because they're all just in the second row on the periodic table, you're done. But if they're atoms from the 3rd, 4th, or 5th row of the periodic table, as sulfur was, you should check the formal charges of all the atoms. And if you have atoms with positive and negative formal charges, you need to double bond them so their formal charges go down to 0, because that's going to be a more accurate representation of the true bonding in the molecule. Now this tells you that, oh, we would predict the bond strengths of the SO bonds to be the same strength as SO double bonds, not SO 1.5 bonds. Now, let's even predict the shape of this molecule. We're going to use a new theory, the VSEPR theory. Look at the central atom, because that's really what determines the molecular shape. And then let's calculate what its steric number is. Now, not individual bonds now, but it's bonded atoms. So how many bonded atoms are there to the sulfur? 2, a left O and a right O. How many lone pairs does the sulfur have? Not how many lone pair electrons, how many lone pairs? 1. So the steric number of this central atom is 3 because the sulfur has 2 bonded atoms and 1 lone pair. So when you have 2 bonded atoms and 1 lone pair, that's a steric number of 3. Those 3 groups always spread themselves out like we did before in BH3 as a trigonal planar shape like this. The O's take 2 of the spots, the lone pair takes the other spot like this. Now, if you talk about where the outer orbitals are on the sulfur, we would say the orbital geometry is trigonal planar. But the question usually isn't what is the orbital shape of the molecule, it's what's the molecular shape. That just means where the atoms are. So if I ask you what's the orbital shape, you could say trigonal planar. But the molecular shape is just the shape determined by the 3 atoms in the molecule, not the lone pair. So look at the O and the S and the O. What shape do they appear to be making to you? Doesn't look very linear to me. What do you think that shape is?
And
Looks angular, exactly. Or some people call it V shape. Our textbook calls it bent shape. They're all the same. Now, what's the angle here? What's the 120-degree angle that Ms. Garcia and Ms. Tennell said for the BH3 molecule? Because anytime you make a trigonal planar geometry, the bond angle is going to be 1/3 of a circle. So the bond angle is going to be 120 degrees here, okay? You want to draw a picture of this. The molecular shape would just be drawing where the atoms are. So you draw that bent shape between the S and the O's and you leave the lone pair off. And this would be the description of what the shape of the molecule looks like. So there actually are two terms when you're talking about shapes or geometries. Orbital geometry would be what's the arrangement of all the lone pairs and the atoms all together. In this case, it'd be trigonoplanar. But molecular geometry just means where are the atoms with respect to each other, and the atoms are making a bent shape here, not a trigonoplanar shape, okay? Now, there's going to be 3 common molecules I'm going to introduce today that I'm going to want you to know their names for. The first one is CH4. It's actually the major ingredient in natural gas, which you use in your stoves at home and your furnaces, and we use in our Bunsen burners when we return to class next week. The name of this hydrocarbon gas is methane. I'd like you to know that, M-E-T-H-A-N-E. So I'll refer to it as methane from now on, and I'll expect you to know this is its formula. The total number of valence electrons in methane would turn out to be 4 from carbon and 1 from each of the hydrogens, 8. The skeletal structure looks like this, and lo and behold, that uses the 8 electrons, so all the valence electrons have been used up. Fortuitously, the carbon gets an octet. The hydrogens all have duets, so this would be the best Lewis representation for the methane molecule. Now, once we've drawn this, we can now try to predict the shape by using the VSEPR theory. So the carbon, which is the central atom, is bonding to 4 hydrogens, and I don't see any lone pairs. So we would say its steric number is 4. 4 bonded atoms and no lone pairs. And if I ask you, how do you think you can spread out 4 repelling groups, these 4 hydrogens, as far apart as possible to minimize their repulsion, a lot of people would look at that Lewis structure and go, wow, those hydrogens spread out pretty far apart. They're like 90 degrees apart from each other. I bet that's going to be the shape of the molecule. It actually makes a flat square. They would actually call that square planar if you just want to make a fancy name for it. But if you think this is the shape of the molecule, that means you are a very two-dimensional person, and you like thinking in 2 dimensions, where the real world is in 3 dimensions. So if you imagine the hydrogens spreading out over all 3 dimensions, you can get a shape that isn't square planar, but is a shape that allows the angle between the hydrogens to be bigger than 90 degrees. You can make it be as big as 109.5 degrees if you spread the hydrogens out in an arrangement like this. If you look at the red lines here, they're showing a geometric 3-dimensional figure called a tetrahedron. It's called a tetrahedron because tetra means 4. It is a solid figure made up of 4 equilateral triangles. There's 3 equilateral triangles around the top and 1 equilateral triangle on the bottom. Well, if you put the carbon in the center and you have the 4 hydrogens point to the 4 corners of the tetrahedron, the hydrogens are now 109 degrees apart from each other, 109.5, which spread them out a whole lot more than this shape where they're only 90 degrees apart. So we would predict from the VSEPR theory that in order to minimize the repulsion between the hydrogens, the methane molecule will form a shape that's a tetrahedron, or using the adjective tetrahedral, because that allows the bond angles to be 109.5 degrees. Now, what if you need to draw the shape of this molecule? This is where your artistic skill is going to come into play now a bit in this course. Now, if you had art masters in elementary school, you've probably learned how to do perspective drawing, but if you didn't, and I never taught you art masters when I was teaching at the elementary schools every once in a while doing that, here's how you're going to do a 3-dimensional picture of a tetrahedron with using 2-dimensional paper. What you're going to do is you're going to draw the carbon on the paper, and you're going to make the bond of the top hydrogen a regular dash, normally as we do in a Lewis structure, because that's going to infer that that bond is on the paper. So carbon bonding the hydrogen straight up on the paper. Then you can go either to the left or the right, depending on whether you're left-handed or right-handed. I'm going to go to the right. I'm going to make my second bond to a second hydrogen as a straight line, meaning that's on the paper. So this structure showing this H, this C, and this H are all on the paper. What's the angle I've drawn here? Can you tell? What do you think? Geometry skills, what angle does that look like?
120.
So I would say it's more like 109.5, but 120 is close, but it's supposed to represent 109.5. So if you think it's about 120, that's within margin of error. I just don't want you to draw this molecule with the hydrogen going like this. Because if you do the hydrogen straight out to the right, what angle are you drawing for me?
90 degrees.
And I bet Mr. Gomez would go, hey, I can tell that's a 90-degree angle. That's not 109.5. And so if I have Mr. Gomez grading your tests next time, he's going to mark that wrong for everybody, okay? So I want to see this looking like as close as it can be to 109.5. And if you do about 120, I don't have my protractor out, I won't be able to tell. But that's how you draw the first half of your methane molecule. Now look over here on the right side. See this hydrogen? This is coming out towards you. See that hydrogen? It's going back behind the molecule. So how do you draw hydrogen so it looks like it's coming towards you? Well, this is your artistic skill. You've got to make the bond look like it's getting bigger because it's getting closer to you. So you draw a wedge so that looks like, oh, the hydrogen is coming out towards me, and now it looks three-dimensional. What about the hydrogen going back behind the molecule? You draw the bond as a dotted line, and actually you make the dotted line kind of recede away would even be better, but I couldn't do that on PowerPoint. I think I actually learned how to do it later. This one I didn't, but I may have some receding dotted lines you'll see later. But that puts the hydrogen so it looks like it's going behind the molecule or behind the plane of the paper. So when you need to draw three-dimensional structures, if you want an atom to be in front of the paper, the bond is going to have a wedge. If you want the atom to be behind the plane of the paper, it's got to be a dotted line. Anytime you draw a bond, when you're drawing a molecular geometry or molecular shape, if you draw a straight bond line as just a dash, I'm going to think it's on the paper. So if you do this as a straight line and this is a straight line, I would think that you have a 120-degree angle here, then a 13-degree angle there, then a 109-degree angle there, and that's not right. Okay? So that's how I want you to draw a three-dimensional tetrahedron with a two-dimensional piece of paper. Okay? The second common molecule I want you to know its name for is NH3. This is called ammonia, A-M-M-O-N-I-A, not to be confused with the polyatomic ion ammonium, which is NH4 positive. Ammonium, one of the polyatomic ions you will need to know for our nomenclature quiz, which will happen next week when we return back to campus for labs, and you'll be coming to lab on either Monday or Wednesday next week, depending upon whether you're group A or B. When you come to lab at 3 o'clock, boom, the first thing we're going to do is you're going to take your nomenclature quiz. And so I'm going to give you 20 compounds, and half of them I'll give you the name and ask you to write the formula. And the other half I'll give you the formula and ask you to write the name. And you've got to get 17 out of the 20 right to pass that quiz. So we'll do that right at the beginning. You'll have with you a blank periodic table. It'll just have the elemental symbol and the atomic number and the molar mass on it. So you'll need to know your polyatomic ions. You'll need to know your elemental symbol name equivalents so that you can actually complete the quiz. So that'll be for next week. So if you're group A, we'll take the test on Monday on campus is correct. And if you're in group B, you'll be taking the quiz on Wednesday. So if you need to practice, that would probably be a good idea. Go back and look at activity 6 that I handed back so you can see what you missed to make sure you understand that. If you want more practice on nomenclature, go to our class website under handouts, not the Canvas page, but my class website. Go to handouts. Handout 3 has a whole bunch of practice for naming and writing formulas of compounds. I think the first page, I have all these ions names, and the second page has their formulas. Then the third page has all these compounds that are ionic, and the fourth page has their names. And then the fifth page has like covalent compounds and acids, and the sixth page has their names. And so you can start on page 1 and then look up the answers on page 2, or start on page 2 and look up the answers on page 1. You can work on doing name to formula or formula to name. Hours of fun by doing that, okay? And Mr. DiFilippo asked, well, we only have to know what is on the handouts. So there, Mr. DiFilippo, there's like 118 elements. So there's probably about, I don't know what, 118, 150 possible cations that can exist. With all the polyatomic ions you know, there might be maybe 50 or 60 non-metal cations you can have. So any compound can be a combination of any cation and any anion. So if you go 150 times 50, I think that would give you the total number of possible compounds that could be on the test. So the chances are every single one that's on the handout and every single one that's on activity 6 will probably not be the ones that'll be on the quiz next week, because I'm just going to pick ones that you don't necessarily have seen before, but I want you to understand how you write formulas and how you name them. Does that make sense? So you're not going to just memorize, gee, when sodium goes with chlorine, I better memorize NaCl. need to understand sodium's +1, chloride's -1. Oh, I only need one of each. If you understand the concept, you can name and write formulas of thousands of compounds, not just specific ones you memorize. Mr. DiFilippo, is that good?
Yes.
So let's go back to our molecular shapes. If you want to predict the molecular shape of NH3, you need its Lewis structure first, and without spending the whole time doing that, this would be the correct Lewis structure for NH3. The Lewis structure does not tell you the shape. You have to determine the steric number of the central atom, and then we apply the VSEPR theory. So the nitrogen has 3 atoms bonded to it, and it has a lone pair. That means its steric number is 4, because you always add up the bonded atoms and the lone pairs. Anytime you have a steric number of 4, no matter whether it's atoms or lone pairs, those 4 groups will always spread themselves out in the exact same way as a tetrahedron. So the orbital geometry of anything with a steric number 4 is always tetrahedral. But what's the molecular geometry? Because when you have lone pairs, once again, you ignore the lone pair and you try to describe where are the atoms with relationship to each other. So the hydrogens are making a little triangular base, and they're coming up to this nitrogen at the top of what looks like a little pyramid. So this is a triangular based pyramid, and so we call this shape trigonal pyramidal. It's not called tetrahedral, that would be the orbital geometry. The molecular geometry or molecular shape would just be defined by where the atoms are, and we call this trigonal pyramidal. The angle would be the tetrahedral angle of 109.5, although interestingly enough, when we measure the angle in the ammonia molecule experimentally, it's actually only 107. Why is that? That has to do with how the electrons exist when they're in bonds and when they're in lone pairs. So watch this. See this red dash here? That represents 2 electrons. Who's attracting those electrons? The nucleus of the nitrogen and the nucleus of the hydrogen. So the electrons stay right here in this narrow space so they can be near those 2 protons. The electrons in this red dash attract to the nucleus of the nitrogen and the nucleus of the hydrogen. So they stay right in that narrow region of space there so they can attract both to the left and the right. And the same thing here. They stay in this narrow region so they can attract to the N and attract to the H. See the lone pair? It's attracting to the N and it's attracting to the, oh, there's nothing up there. It's only attracting to the N. So guess where it goes? It goes down flat onto the N and sort of covers it. It spreads out. You ever been in an airplane flight and you're sitting in one of the seats and then like somebody from the LA Rams shows up and he's 6'6", 290 pounds and he sits in the seat next to you? What happens to you? You get crushed over because he takes up so much space, right? Well, this lone pair is like a LA Rams football player. He takes up so much space around the nitrogen that these hydrogens all get crunched together and it makes their angle shrink a little bit. So anytime you have lone pairs in molecules, the theoretical angles are usually not the measured angles we get. So I would like you to know that as long as there's a lone pair, the bond angle may not be the perfect 109.5. It's probably going to be a little bit less. What exactly is it going to be? I don't know. Every molecule is different. I wouldn't expect you to memorize those, but just realize that if you see a 107, it doesn't mean the VSEPR theory is wrong. It just means, oh, that lone pair is doing some extra repelling, so it's just pushing the hydrogens a little bit closer together. Okay? So here's how you would draw the molecular shape. You just leave the lone pair off on the top, but this is essentially what we drew as a tetrahedron earlier, but I'm leaving the one of the 4 positions where the lone pair is, was sticking on. I put the lone pair on the top. You could put it in any one of the 4 spots. A tetrahedron is perfectly symmetrical. If I would have put the lone pair over here on the right side, the shape would still be trigonal pyramidal. This would be the top, and the 3 hydrogens in the base would be over here. So perfectly symmetrical, so you can take the lone pair off any position here and put the hydrogens in the other 3. It's always a trigonal pyramidal shape. It's just sometimes it's kind of harder to see it, but it actually would be. The third molecule I want you to know its common name for is this one. This one's called water, W-A-T-E-R, okay? And the Lewis structure for water looks like this. And so if we're going to try to predict the shape for water, we have to once again determine the steric number of the central atom and then come up with the VSEPR theory shape. The oxygen in the center has 2 atoms bonded to it, and it has 2 lone pairs. That means its steric number is 4. 2 bonded atoms, 2 lone pairs. Anytime you have a steric number of 4, those 4 groups will always repel themselves out into a tetrahedral geometry. We would say the orbital geometry of this molecule is tetrahedral, But the molecular geometry or the molecular shape is not. The molecular shape is defined by only where the atoms are. So look at the hydrogens and oxygens in this tetrahedral arrangement here. What geometrical arrangement do these H's and O's look like they're in to you? What do you think? What is that shape? That looks like a bent shape, exactly correct. So water would be expected to be a bent molecule, theoretical angle 109.5. Mr. DiFilippo should not be surprised to learn the angle isn't 109.5, it's less. He should even be not surprised to learn it's less than 107. It's closer to 105 because there's two lone pairs. It's like a three-seat place in the on an airplane flight, and two of the three spots are taken up by defensive linemen on the LA Rams, and you're going to really be crushed. So the angle actually comes out several degrees lower than you would expect. You want to draw a bent shape, then you just make sure you look like the hydrogen angles are less than 180 degrees, and this is what the two hydrogens would look like if I pick them in this particular spot here. Okay. So these are the different types of geometrical orbital geometries and molecular geometries you can have for steric numbers of 4. This is the first molecule now that's going to have a steric number higher than 4. PF5, phosphorus pentafluoride, has phosphorus bonded to 5 fluorines, which on the first approximation looks like it's disobeying the octet rule. So Lewis would have been really upset with this molecule way back in the 1910s. But now realizing that phosphorus is in the 3rd row of the periodic table, it has d orbitals in its outer shell. And so if it has d orbitals in its outer shell, then that means it can make extra bonds that can exceed the octet rule. So if you add up the valence electrons for this, which there'd be 40, draw the skeletal structure with phosphorus in the center, 5 fluorines bonded to it, and then fill in all the lone pairs till you get to 40 electrons, you get a structure that looks like this. All the fluorines have octets, and the phosphorus has an octet. Or the phosphorus exceeds the octet rule, but it's allowed to do that because it has d orbitals in its outer shell. Anytime you have a central atom that can exceed the octet rule, you probably want to actually calculate its formal charge to see if maybe the molecule should have double bonds in it. So if we calculate the formal charge of the phosphorus, phosphorus naturally has 5 valence electrons, and then it's making 5 bonds, and it has no lone pairs. 5 minus 5 minus 0, the phosphorus's formal charge is 0. The fluorines also have a formal charge of 0, 7 natural valence electrons. They're making 1 bond each, 6 lone pair electrons, so 7 minus 1 minus 6. So every atom in this molecule's Lewis structure has a formal charge of 0, so we would not make any double bonds. This would be what we would say to be the most accurate Lewis representation for this molecule. Now, how do we determine the shape? We go to the central atom, we determine its steric number, and you should see, oh my gosh, the steric number here is 5 because there's 5 bonded atoms and no lone pairs. So now we have to try to imagine how can 5 repelling groups spread themselves out as far apart as possible. And it turns out it's not a perfect little shape like a tetrahedron was, but it actually is very symmetrical. It actually looks like this. What it is it's 2 pyramids on top of each other. This is a triangular-based pyramid pointing up, and this is a triangular-based pyramid pointing down. Because this is a structure that has 2 trigonal-based pyramids, it's called trigonal bipyramidal. And if you put the phosphorus in the center and you point the fluorines to every corner of this, 1 fluorine to the top, 1 fluorine at the bottom, and then 1, 2, 3 around the middle, then you will have spread out those 5 fluorines as far apart as possible. And the name of the shape is trigonal bipyramidal because it's a double triangular-based pyramid. Now, because it's not perfectly symmetrical, there are actually 2 different types of positions in trigonal bipyramidal geometry. If you imagine this is the Earth, okay, here's the Earth. What goes around the center of the Earth like this? What's that line called? Think back to geography. What's that called?
Equator.
The equator. See these 3 fluorines here? These are called equatorial fluorines because they're on the equator if you sort of picture this as the Earth. So the 3 equatorial fluorines that are going around the center are 120 degrees apart from each other because they're 1/3 of a circle. Okay. Now, if you imagine this is the Earth, here's the North Pole at the top and the South Pole at the bottom. What's the line that goes through the North Pole and the South Pole called? The Earth's spins on it. Earth spins on its
Access.
That's right. Wasn't some Oingo Boingo song talking about that? So those fluorines on the top and the bottom are called axial fluorines because they're on the axis. If you imagine this as the Earth, what's their angle? They're 180 degrees apart from each other, but they're 90 degrees away from the equatorial plane. So all the angles between the fluorines are not identical. You have the equatorial fluorines that are 120 degrees apart from each other. You have the axial fluorines, which are 90 degrees apart from the equator and 180 degrees apart from each other. So two distinctly different types of fluorines. That's going to cause some interesting things in the next couple of molecules. So steric number 5, all bonded atoms, you're going to wind up having a molecule whose shape is trigonal bipyramidal. How do you draw that? The axial fluorines are on the plane of the paper. You draw them as straight lines. But now for the equatorial ones, you pick one to be on the plane of the paper. I've picked it pointing to the right. And if this one's on the plane of the paper, what are these two doing? One's coming towards you and one's going back behind the molecule. So one you draw with the wedge so it looks like it's coming towards you. One you draw as a dotted line so it looks like it's going back behind the molecule itself. That's how you draw a two-dimensional representation of the three-dimensional trigonal bipyramidal shape. Okay. This molecule, sulfur tetrafluoride, has a total of 34 valence electrons in it. If you draw the skeletal structure with sulfur in the middle, bond 4 fluorines to it, and fill in all the fluorine octets, use up 32 electrons, yet there's 2 electrons left over. You have to put those in the outer shell of an atom that can exceed the octet rule, which is the sulfur, because it's in the 3rd row on the periodic table. It has d orbitals in its outer shell. So notice my sulfur has a lone pair squeezed into its outer shell there, okay? A lot of people, when you get to the last 2 electrons, like those last 2 I have on the sulfur, will make a double bond with it. Never do that. Always put all the valence electrons in as lone pairs, and then once all the electrons are in as lone pairs, then make double bonds if you have to. How do you know if you're gonna need to make double bonds or not? You calculate the formal charges. Mr. Gomez asked, do you only find the steric number for the central atom when you're trying to determine the shape of the molecule? Yes, but you can determine the steric number for any atom in any molecule. Take this fluorine, for example. If I asked you what is its steric number, you would say 1 bonded atom, 3 lone pairs, it has a steric number of 4. So you can calculate it for any atom, but the central atom is important because its steric number determines the molecular shape, and that's why we're focusing on that. But we will eventually, as the week progresses and we move on to next week, we'll be talking about steric numbers of every single atom in particular molecules. So how do we know that this lone pair should not be a double bond? We'll check the formal charge of the sulfur. Sulfur naturally has 6 valence electrons. It's bonding to 4 atoms. It has 2 lone pair electrons, 6 minus 4 minus 2, its formal charge is 0. So if the central atom's formal charge comes 0, and you can check the fluorines, they're zeros also, then you do not make double bonds. This is the best representation because when all the atoms have 0 formal charges, that's as accurately as you can draw it. Now, we did the steric number for the fluorine, which Mr. Gomez asked, and it was 4. The central atom's steric number turns out to be 5 because there's 4 bonded atoms and that pesky lone pair. So if you have a steric number of 5, we now know how these 5 groups will spread out as far apart as possible. They'll spread out in a trigonal bipyramidal geometry. But now something becomes really interesting. Where are we going to put the lone pair? Because all positions in trigonal bipyramidal geometry are not equal to each other. You know, some positions are more equal to others, if I paraphrase Animal House. So here, if I put the lone pair on an equatorial position, I would have a molecule that looks like this. So notice I put the electron pair in one of the 3 equatorial positions, and then the fluorine atoms occupy all the other spots. But what if I put the lone pair in an axial position instead, like this? That molecule has a completely different shape than the one on the left. One of those is right, and one of those is wrong, okay? So what's happening here? How do we figure out which is right, which is wrong? We've got to figure out which one has the least amount of repulsion. So remember who's more repulsive. It's the one that takes up all that space near the central atom. The lone pairs are the most repulsive. So this is going to repel against anything near it. This is going to repel against anything near it. And what are the closest interactions it can have? It's only 90 degrees away from this top fluorine and 90 degrees away from the bottom. So those are pretty close. How far is this interaction here? That's 120 degrees, so that's further away. And this one, although it looks further, if you were in second grade, you wouldn't be able to understand this, but because you're older, you can. This is still 120 degrees also, because it's 120, 120, and 120. So this lone pair is 120 degrees away from each of those, but the close interactions are the ones at the top and the bottom. You're going to focus in on the close interactions only, the ones that are repulsive, that are close. So this lone pair is repelling 90 degrees to that, and it's repelling 90 degrees to that. So this arrangement allows two close 90-degree repulsive interactions. But let's go to the other structure where we put the lone pair in the axial spot. How many 90-degree repulsive interactions does it have? Well, it has one over here, and one to the front, and one to the back. Oh my gosh, that's 3 90-degree repulsive interactions. That's more repulsion. That's bad. Therefore, this one must be the most stable configuration because it has the least number of close interactions. So this is the wrong shape for the molecule. The correct shape is the one we have drawn on the left. You will find this always works out this way in a steric number 5. You always want to put the lone pairs in the equatorial positions because they're always only going to repel 90 degrees against the top and the bottom. If you ever put a lone pair on the top, it's always going to repel 90 degrees to 3 in the equatorial positions. That's always going to be worse, okay? So what's the shape of this molecule? Well, if you take your head and turn it 90 degrees to the right, you will see that the molecule looks like a seesaw back from your childhood days, okay? And in this seesaw shape, it's a seesaw shape because we put the lone pair in the equatorial position. You find in steric numbers of 5, we're always going to put the lone pairs in the equatorial positions. That's always going to give you the shape with the least amount of repulsion. If you want to draw this geometrically, we draw the axial positions up and down as straight lines, but the 2 fluorines that are on the left, one is coming towards you, you draw its bond as a wedge. One's going behind the molecule itself, so you draw its bond as a dotted line, okay? Next molecule is chlorine trifluoride. Total number of valence electrons is 26. If you draw the skeletal structure with chlorine in the center and you bond 3 different fluorines to it, you're going to wind up having 24 electrons when you fill out all the octets. So we have to squeeze an extra lone pair into the outer shell of the chlorine. So the correct structure looks like this. Steric number of the central atom, 1, 2, 3, 4, 5, because it has 3 bonded atoms and 2 lone pairs. So we're still going to have these 5 groups arranged as a trigonal bipyramidal geometry, but you have to think about where are the lone pairs going to go, and it's always better to put them into the equatorial position. So I'm going to put them in 2 of the 3 equatorial positions like this, and this will be the predicted most stable configuration for this molecule. If you want to determine the shape of this, turn your head 90 degrees to the left, and you will see the letter T. That's called T-shape. Okay, drawing it would look like this. All the atoms can be drawn directly on the paper, so there are no wedges, there are no dotted lines. Okay. The next one I want to do is a molecule with a noble gas. Since the 1960s, people have taken noble gases, which before that time had never made any compounds. They put them under high pressure, high energy, and with the active element fluorine, and they forced them to make compounds. So there are compounds that exist that contain noble gas atoms. The correct Lewis structure for this has so many electrons, it actually has, how many does it have? It's 14, 22 electrons, that once you fill the octets for all the atoms, you have 2 electrons left over, has to be squeezed into the outer shell of the xenon, and so the xenon exceeds the octet rule. Do we need to make double bonds on this? Well, if you calculate formal charges, you will see that all the atoms have 0 formal charges, so no double bonds necessary, okay? So if we want to predict the shape, we're going to use the VSEPR theory. The central atom has a steric number of 5 because it has 2 bonded atoms and 3 lone pairs. So if we arrange those lone pairs in the most least repulsive places, which are in the equatorial positions, you get a molecule that looks like this. So you tell me what's the molecular shape of xenon difluoride? What's that shape? Look at the atoms. How are they arranged? Linear is exactly correct. So there's the molecule. And if you don't want to draw it up and down, you can certainly draw it horizontally. That would still be a line. That would be perfectly fine. Okay. The last steric number I want to talk about is steric number 6. This is as high as we're going to go. So if we try the molecule sulfur hexafluoride, which is actually a gaseous substance, it's a very dense gas. And if you've never heard of that before, you should really go on YouTube and type in sulfur hexafluoride. I think it'll entertain you for a little bit. You'll like that. But if we draw the correct Lewis structure for this, and I'll try to save some time as we're trying to finish up here, this would be the correct Lewis structure. All the atoms have formal charges of 0. The sulfur is exceeding the octet rule, but it can do that because it has d orbitals in its outer shell. To predict the shape of the molecule, we'll use the VSEPR theory. We'll calculate the steric number of the sulfur first, which turns out to be 6. There are 6 bonded atoms, no lone pairs. And so the most efficient way to spread out 6 repelling groups is in a geometric arrangement like this. This shape is called an octahedron because it has 8 equilateral triangles as faces. Can you see them? There's 4 on the top, 1, 2, 3, 4, and then 1, 2, 3, 4 on the bottom. If you put the sulfur in the center and have the fluorines point to each of the corners of the octahedron, then these fluorines will be about 90 degrees apart from each other if they're close and 180 degrees apart from each other if they're across. So this is the most efficient way to spread out 6 repelling groups as a shape called an octahedron, or octahedral is the adjective, where the fluorines are 90 degrees apart if they're close, 180 degrees apart if they're directly across from each other. If you want to draw this, we have the fluorines up and down that are on the plane of the paper. But over here, I've got these 2 fluorines in front of the paper, those 2 fluorines behind. So I draw 2 wedges for the front 2 fluorines, 2 dotted lines for the back 2 fluorines, and that allows you to draw a 3-dimensional picture with a 2-dimensional piece of paper. Okay? Continuing on with steric number of 6, we have 2 examples left. So I know we're up to 240 now. If you need to go, I understand completely, but if you can stay for a few more minutes, we'll finish this up pretty quickly. The next molecule is iodine pentafluoride, where there are so many electrons that once you draw the Lewis structure and fill in all the octets for all the iodines, you'll have a pair of electrons left over. You squeeze those into the outer shell of the iodine. I should have said all the fluorines, you fill their octets. Then you put the extra lone pair in the outer shell of the iodine. You don't put it in as a double bond. And then once you've put all the extra electrons in as lone pairs, check the formal charges. And it turns out everybody has a formal charge of 0 on this. So this is a good Lewis representation of the molecule. The iodine has a steric number of 6 because it's bonding to 5 atoms and has 1 lone pair. So these 6 groups will spread out in an octahedral shape. So the orbital geometry is going to be octahedral, but what's going to be the molecular geometry of the molecular shape? You just have to replace one of the positions with a lone pair. And it doesn't matter which one you do because equatorial and axial positions are not different for a steric number of 6. It's a perfectly symmetrical molecule. So if I want to put the lone pair over here, the molecule is going to be the exact same shape. It's just easier to see when I put it down here. We have a square here in the middle going up to a top. This is a square-based pyramid. So the molecular shape is called square pyramidal. Okay? If you want to draw a square pyramidal shape, you draw it just like the octahedron we had before without the 6th atom pointing below. And so this would give you your square-based pyramid, much like the ones found in Egypt and Mexico City, right? And then coming up to this fluorine at the very top. Okay? And then the final molecule I want to show you is xenon tetrafluoride. Xenon tetrafluoride has so many electrons that when you fill the octets for all the fluorines, you actually have 4 electrons left over. So you need to add 2 extra lone pairs into the outer shell of the xenon. So you can see I've squeezed those in there. And now that all the lone pairs are in there, if you calculate the formal charges of all the atoms, everybody's formal charge comes out to be 0. So no double bonds necessary. The xenon's making 4 bonds and has 2 lone pairs. So therefore its steric number is 6. And if it has a steric number of 6, we know these the repelling groups around the xenon will arrange themselves in an octahedral shape. The question is, where do you put the lone pairs? You have 2 choices. They can be across from each other, or they can be 90 degrees apart from each other. Which do you think would be less repulsive?
180 degrees apart from each other.
Because the lone pairs repel each other most, you don't want to put them close to each other, you put them across from each other. So when you do, if you look at where the atoms are arranged now, the atoms are just making a square. And because it's a flat square, we call the molecular geometry square planar. And if you erase the lone pair on the top and the bottom, you have that square planar geometry. Okay. So homework, go ahead.
How are they making a square? Oh, never mind. Is square planar the orbital geometry?
No, that's the molecular geometry. The orbital geometry is octahedral. You count all the lone pairs when you're doing the orbital geometry. There's an orbital pointing.
Oh, and then molecular is where you ignore them?
Yes, the molecular geometry is where you ignore the lone pairs.